Alright, so I uploaded homework 8 yesterday, and that's the last homework, and that's due Thursday of next week. So whatever that day is, it's 25. And then midterm 3. April 26th. It's a homework 7 and 8. And then there's no final. There is a final project. Due someday. Let's see if it's due. Alright, so if you go to the course website, there's a part that says final project. And so here's the link to the PDF. So there are 8 questions. Some of them are worth 15, some of them are worth 30. For your final project, you want either to pick 2 15-pointers or 1 30-pointer. Okay, so you can read what the programs are here. Some of them make more sense to write in Java, some of them make more sense to write in Python. Yeah, one of them is just program Kruskal's algorithm. This one's kind of easy. All right. So that's where you can find the final project questions. Some of the questions reference a PDF, and you can find like question 6 references this thing, and question 7 references that one. I think this is just lecture 7C or something. 8C. Yeah. So this one is also on the to do that. So we're, just getting close to the end of the course. So this is basically the things for you left to do. Homework 8, midterm 3, final project. Of course, that's if you've already completed the 7 homeworks that have been posted so far. I think homework 7 was already due. Yeah.
Are you gonna check all the homeworks as of April 25th, or as of the final date?
I think like final day of class.
Okay.
So like April 29th.
Okay, thank you.
Yeah. Any other questions? No. All right. Okay. So last class we did topological sort. And a bit of graph theory stuff. There's one more graph theory thing left to do, but I'll do it Friday. Let's get to dynamic programming. We did some dynamic programming already. I don't know if you remember the dynamic programming example I did in class with the problem where you have the numbers from 1 to 144, and then Alice picks a number from that set. And then Bob chooses a set, a subset A of S, and if, say this number is called N, if N is an A, Bob pays $2, and if N is not an A, Bob pays $1, and then the question was, what's the smallest cost to guarantee that Bob finds Alice's number? So we worked on this problem, it was more than a month ago. The solution was with dynamic programming. So lecture 8 is about dynamic programming. And basically the gist of it is when you have something that's a recursion, one way you can speed up your program is by storing the outputs, usually in an array or something like that. So in this case, if you change 144 to some number m, well, it's easy to calculate that f of 1 is 0 because there's only one number, so Bob knows what number Alice picked. F of 2 is $2 because Bob has to pick a subset, and if he guesses correctly, then it costs him $2. If he's incorrectly, then it's better off right now because it only costs $1. But in the worst case, it costs him $2. That's what we're keeping track. Then for f of 3, so if Bob picks something of size 1, and he's, let's say something of size 1, something of size 2, if he guesses correctly, then it costs him $2. If he guesses incorrectly, it costs him 1. But now, at the end of the day, it'll cost $3. If you went this way, then the cost of 2 is 2. So it'll be 1 plus 2. If you have like 4, you could split in 1, 3, or you could split in 2, 2. In this case, the cost is $2. In this case, the cost is $1 plus f of 3, which is 4. Here, you would get $1 plus f of 2. Here you get $2 plus f of 2. So this is 3, this is 4. So the highest number of all of these is 4. That means f of 4 is 4. And if you want to find f of 5, you have, so 5 can be split in 2 ways. You can split 1, 4, or you can split 2, 3. And here you guessed it right. You're super lucky. You only paid $2. Here you guessed wrong, so you paid $1, but then you also have to pay whatever the cost of figuring it out for 4 is. So that cost was 4, so this comes out to 5. Here, this would be 2 plus f of 2, which is 4. This is Actually, this strategy is the good one, right? Because worst case scenario, you get 4. With that strategy, worst case scenario, you get 5. So you can guarantee paying just 4 if you follow that strategy. So this was a problem. We talked about it about a month ago. And so you can come up with a recursion where basically f of m is, so you split m in a and b, where a is less than or equal to b. And the cost of this one would be 2 plus f of a. And the cost of that one is 1 plus f of c. So for all a's between 1 and m over 2, you test the maximum of 1 plus f of m minus a and 2 plus f of a. So you compute the max of these two, but for each value of a, and then among all those values you compute the minimum. So the formula is kind of complicated. It's easy to code. But if you just code the recursion, it will not run fast. It won't be able to do this 144 one. It's too expensive. So what you have to do is you do dynamic programming where you store the values you've already computed. So you just go in order. You do f of 1, f of 2, f of 3, f of 4, f of 5. And by storing these numbers, it doesn't calculate them over and over. So what do I mean? So imagine you have the 144, and let's just pick one of the ways to cut it. Let's grab it as 140. Well, let's do 60 and 84. So this one, you have to compute 2 plus f of 60, and here you have to compute 1 plus f of 84. Obviously the 1 plus is easy, but the f of 84, well, how do you do f of 84? 84, you have to break it into 2 pieces and calculate, right? So let's say you break it, one of the pieces you break it into is maybe, let's say, 40 and 44. That's just one of them, right? There's more. So you have to calculate at some point 1 plus f of 40, and you have to calculate, 2 plus f of 40, 1 plus f of 44. But over here, when you're computing 60, you also have to do 20 and 40. So you have to calculate 1 plus f of 40 at some point. So if you just do recursion, when you calculate this f of 40, you do it in the tree that came out from 60, but you also do it in the tree that came out from 84. And you can kind of picture, you're going to compute it so many times, that f of 40. So if you store the answer the first time you calculated it, then anytime your code sees f of 40, it knows what it is. It doesn't have to do all the trees. It just says f of 40 is 7, so I'll just plug in 7. So it's like a very simple idea, this dynamic programming. Like when I heard that this was the name for this idea, I was like, wow, that's a pretentious name for such a simple idea. But the idea is just, whatever you computed, you store it. And when the computer needs it, it's already stored, so it can just retrieve it quickly. So this is a very useful technique whenever you have recursion. And if you read the notes on Moodle, the example is like the Fibonacci example. So Fibonacci numbers, you can do it with, well, I guess basically just the example is Fibonacci. If you read those notes from Moodle, they're kind of written in how you would do it in Java. So if you like Python, then you import a library. It's called functools, and don't have the details with me now, but I did give them to you a month ago. And I think they're in an email as well. Okay. So that's dynamic programming. Let's do an example where it comes up. All right. Any questions about the idea of dynamic programming? Awesome. All right, so we've talked about matrix multiplication before. In particular, we did Strawson's method to compute the product of two big matrices. But now we're going to analyze something else. So let's think of multiplying a bunch of matrices, right? So let's say you have to multiply A times B times C times D, and you have 4 matrices you want to multiply. And in this example, we're going to let A be a 20 by 2 matrix, B will be a 2 by 30 matrix, C will be a 30 by 12 matrix, and D will be a 12 by 8. Let's just assume that if you multiply an M by N matrix with an M by P matrix, you need M times N times P operations. Well, let's change it to maybe multiplications. Okay, it's not so hard to see why. So if you have like 3 by 2, sorry, this 2 by 3, let's say. And then you have a 3 by 4. Okay, so 3 by 4. So when you multiply this, you're going to get a 2 by 4 matrix. So for this top value, you do the scalar multiplication of this vector with that vector. So that entitled 3 times 3 operations. And then this by that. And this by this. And this by this. And this by this. But so C11 is A11, B11, plus A12, B21, plus A13, B31, and then C12 is A11, B12, plus A12, B22, plus A13, B32, and so on. C24 would be A21, B14, plus A22, B24, plus A23, B3. So like this tells you which row in the first matrix you're going to use, and the other number tells you the column in the other matrix. You multiply everything in this row with that column. But some of these things, because we're thinking of it as dynamic programming, some of them you already calculated, right? So, is there any repeat? Oh, maybe not. Did you do? Oh yeah, they're all independent. Alright. So the number of multiplications we have are, so the number of terms here is 2 by 4, right? So there's 8 terms, and each one of them use 3 multiplications. So the total number of multiplications is 24. So that logic just always extends. If you have an m by n and an n by p, you're going to end up with an m by p matrix. So it's going to have m times p entries, and each entry was formed by doing n multiplications. So that's why you do m times n times p multiplications. Okay? All right. So now let's get to the interesting part. This is what happens when you multiply 2 matrices, or when you multiply more matrices. So the operation of multiplication is a binary operation. It takes 2 things and it spits out 1 thing. So you get 2 matrices, it spits out a matrix. Now we're so used to multiplication from all our life, then we think you can multiply 3 numbers. You can say 2 times 3 times 4. But multiplication is defined for what happens when you multiply 2 numbers. And the reason we can multiply 3 is just because the operation is associative. So if we want to do 2 times 3 times 4, then we do 2 times 3, and then multiply that. Multiply 4 to the output, right? You're not actually doing, like if you write 2 times 3 times 4, we're abusing notation. That doesn't mean anything. It means you multiply something, and then you multiply the output by the new thing, all right? So if you're thinking of A, B, C, D, well, what order of operations will save us time, right? So you could think of it as you multiply A times B, you multiply C times D, and then you multiply those outputs. That's one thing you could do. Or you could do C times D, then B times C times D, then A times that whole thing. Or is there any other thing we could do? I guess we could do this. So here you do CD first, and then multiply by B. Maybe you could do. Yeah, we could also do this. So as you can see, there's a bunch of ways you could do it. Let's just look at these 4 examples and how many operations they take. So we're going to take the matrices to be of this form. Okay, so this first example, so how many operations? Let's see. How many multiplications? All right, so A times B is a 20 by 2 by a 2 by 30. So that takes 20 by 30 multiplications. So it's, 20 by 30 by 2. So that's 20 times 2 times 30. The C times D is 30 times 12 times 8. So that's this multiplication, but we have one more to do, which is the output of this product times the output of that product. So A times B, this thing, would be a 20 by 30 matrix, and this thing would be a 30 by 8 matrix, right? So then the product of these two matrices takes 20 times 30 times 8 operations. Let's see, what do we get? Well, that thing, let's now do this one. So C times D, 30 times 12 times 8. Now C times D is a 30 by 8. 30, B is a 2 by 30. So the product of these two would be 2 times 30 times 8. But now you get a 2 by 8. So this is a 2 by 8, and you're multiplying by a 20 by 2, so you get 20 times 2 times 8. Please make sure you're following where I'm getting those numbers from. If you have a question, now's the time to ask before things get weirder. So this one is 8,880. Let's see this one. That's 3,680. Let's do this one. So, all right, how many operations does doing B times C take?
2 times 30 times 12.
Yes. All right. So now that you have that matrix and you multiply it by D, how many operations does it take? Someone other than Dennis. So first you have to figure out what type of matrix is B times C. So what types of matrix is B times C? How many rows and many columns?
2 by 12.
Yes. So this is a 2 by 12. And D would be a 12 by 8. So how many operations doing a BC times D? So you just do 2 times 12 times 8. There will be, the middle number is repeated, so you just count it once. 2 times 12 times 8.
Okay.
All right, so now BC times D is what type of matrix?
2 by 8.
2 by 8. So then this whole thing is a 2 by 8. 8 times that, how many operations does it take?
20 by 2 by 8.
Alright, so let's see how much does this cost. So that's 1,232. Okay, I'm too lazy to do the next one, but I think you get the gist of it. So which one takes the least number of operations? It turns out that it's this one. And here are the 5 ways. Well, I guess I got 4 of them. Here are the 5 ways you should do it. You could order the matrix multiplication, and the one with the smallest one is 1,000. So coming up with a good algorithm to minimize the number of multiplications would be useful. If you imagine multiplying many matrices then the issue is that the number of ways to do it just grows pretty fast. I think you can, let's see, so this one, is it really just 5? Yeah. So, the number of ways, just considering the number of ways to write all the multiplications, it turns out to be equivalent to the number of ways of putting parentheses. But parentheses have a rule, right, that you cannot have more right parentheses than left parentheses at any time. So if you open parentheses, you can open another one, but you can't like close it twice, right? So you can kind of envision that a left parentheses is kind of like stepping to the right, and a right parentheses is like stepping up. And so if you picture a pathway of doing these types of steps, you basically want the same number of lefts as rights. So you're going, say, from here to here. So you have a path. And because the number of right parentheses can never beat the number of left parentheses, you're looking for a path where you never cross that diagonal. You can touch it, but you don't cross it. And it turns out this is a famous combinatorics question. How many paths are there from 0, 0 to n, where you are allowed to take these steps, but you can't cross the diagonal? And the number is called the nth Catalan number. And the formula for it is 1 over n plus 1 times 2n choose n. So, here. So these are the number of ways to find all the multiplications. But I'm not sure the one with the matrices matches this. Let's see, so C4 would be 1/5 of 8 choose 4. So that's 1/5 of 8 times 7 times 6 times 5 over 4 times 3 times 2 times 1. So you get 42 over 3, which is 14. So that's bigger than 5. Let's see what is C3. Okay, so it looks like if you have n plus 1 matrices, then the nth Catalan number is the one that works for that matrix. So with 4 matrices, you use the third Catalan number. But if we have 5 matrices, then the number of ways to do it would be 14 instead of just 5. So there would be 14 things to calculate. And if you had 100 matrices, then that number is just enormous, right? So C99 would be 1 over 100 times 198 choose 99. Let's see how big that number is. So that's the number of ways. Let's see. So it has 57 digits. Pretty crazy. Okay. Well, let's see, how do you prove this? This is a cool math problem. So how do you prove that the nth Catalan number is that crazy formula? So let's first think of how many paths there are from 0, 0 to AB, where you only allow unit steps to the right and up. So you can't go down, you can't go left. You're always like going in that direction or up. So if you think about, to get from here to there, you need A plus B steps, right? Because you need it to advance. In fact, not only A plus B steps, you need A right arrows and B up arrows. So you can consider like A plus B, the A plus B moves you're gonna do, and you know that you need A of them to be right arrows and B of them to be up arrows, so you can just do whatever you want. And as long as you pick A right arrows and B up arrows, you're going to create a path, and the path will be unique. So this just tells you that the count is A plus B, choose A. Right? You have up all of these, you pick which ones are going to be your right arrows, and you put an up arrow everywhere else. You could also pick the up arrows instead of the right arrows if you want, but these two numbers are the same. And this is one way you can prove that they're the same. Okay, so what we're gonna do is we're gonna consider a path. So a path from 0, 0 to n is good if it does not cross the diagonal. Alright, so you have 0, 0 here, you have n there, you have the diagonal connecting these two, and you have a path that can touch the diagonal but never crosses through. Alright? And we'll say the path is bad if it crosses the diagonal. So our goal is to find the number of good paths, right? So Cn is the number of good paths. But the number of good paths is the same as number of paths minus number of bad paths. So what we can do is we can, maybe it's easier to count the bad ones than the good ones. Let's count the bad ones. So this, I'll do an example with a 4 by 4. 0, 0, 0, 4. Okay, so we have 0, 0 to 4, 4. Let's consider a bad path. Let's do that path, for example. Okay, so what I'm gonna do is I'm gonna change. So I'm gonna look at the first time I cross. And I'm going to switch everything beyond that, where if it was an up, I change it to a right. So instead of this, I'm going to have right, up, right, up, up. Okay? So I look at the first cross. I switch all the right arrows to up arrows and all the up arrows to right arrows from that moment on. Okay? So I like deviate here. And I'm gonna end up at 3,5. So this happens no matter where you are. So if you have this path, then the first time you cross is here and you change one right arrow to an up arrow, you end up at the same spot. Why are you always going to end up at the same spot? Well, if you look at the first cross, that means there's one more up arrow than right arrow. So when you switch what's left was supposed to be one more right than up, but by switching them, you again have one more up than right. So the difference between them two at the end has to be 2. And because their sum is still 2n, they have to end up at n minus 1 and n plus 1. So every bad path, you can manipulate it and force it to end here. So every bad path can be associated with a path from 0, 0 to n minus 1 comma n plus 1. So doing this thing. Now the question is, all right, if I have a path that just gets there, how do I then translate it to a bad path from the beginning? Okay? So what you can do is you look at the first cross and you change all the rights to ups, and now instead of ending there, you're going to end up here. And it's going to be bad because you crossed. And if you end up here, you had to cross, right? Because how do you get here? You can't go backwards, so you have to cross the diagonal at some point. So these are in bijection. For every bad path, there's a path from here to there. For every path from here to there, there's exactly one bad path. So the number of bad paths is the same as the number of paths from 0, 0 to n minus 1 comma n plus 1. But from that formula over there, that's 2n choose n minus 1. Well, let's do n plus 1. Okay, so the number of bad paths is 2n choose n plus 1. So then this formula here, you have 2n choose n minus 2n choose n plus 1. And then we just do simple algebra. So 2n choose n is 2n factorial divided by n factorial times n factorial. 2n choose n plus 1 is 2n factorial divided by n minus 1 factorial times n plus 1 factorial. So we can take common denominator n plus 1 factorial times n factorial, and here you multiply the top by n plus 1, and here you multiply by n, so you get 2n factorial divided by n plus 1 factorial times n factorial. That's 1 over n plus 1 times 2n factorial divided by n factorial times n factorial. That's 1 over n plus 1 times 2n choose n, which is what we wanted to prove. There's another way to do it. We'll do that on Friday or Monday, depending on what I decide. Okay. Have a nice day. See you Friday.